Okay, so my first topic will be about authentication. So let's first start with a few definitions and see how we perform authentication and how we store passwords and actually how we should store passwords. These will be the topics I will talk about. So let's define what an authentication is. It is determining the identity of the person or the process. So in this case, we bind the identity to a subject. Our goal is to ensure that you are the person who you are claimed to be. So generally, there are three ways of doing this. Three ways to establish a user's identity. First thing you can do is, it might depend on something you know. This can be like a PIN number or a password. But generally, people thought that password will disappear at some point, like 10 or 20 years ago. People working in this area thought that it is hard to store the passwords, and probably in a few years they will vanish. But nowadays we have more passwords than ever. So apparently they are not going anywhere. Second thing is that you can establish your identity by using something you have. This can be identity cards, the smart cards we use at our university, or physical keys, tokens, the things that you can put it at the USB port and prove who you are. And the third one is something that you are. These generally based on biometrics such as fingerprints or your iris code. And here there might be some problems also, but let me remind you something about this iris code. In all of the sci-fi movies, in a spacecraft or something, you open the doors by looking at the place, so it scans your eye and you open the door. Or most of the time you put your finger or your hand so that you can open the door. And in all of those movies, somebody cut the arm of a person and opens the door. It doesn't work in real life. Okay, the machines understand if it is a live or a dead hand. So I'm sorry that I'm ruining all of those sci-fi movies for you, but in real life we know that if the eye is alive or dead, or your hands belong to a person who is alive or dead. So this is important, and actually this should also be the information we should spread so that the attackers would not try to cut our arms. Okay, so authentication factors, let's start with something they are useful as long as you remember it and no one can guess or recover it. So this is the important thing about passwords. People forget their passwords all the time, and this is why we are trying to use easy to guess passwords, but it helps the attackers. So there are things you can do about it, and also the designers can do about it. So this will be actually the topic that will be talked most of the time in this lecture. And the second thing is something you have, useful as long as you do not lose or damage it. This is very important because a lot of people bought this kind of devices. You pay like $50 or something, but then all of these devices also ask you to enter a PIN or a password, and then you forget your password. So you just waste your money and resources for such a USB device that you can no longer use. So this is really important. And if you look at something that you are, in this case, the precision of its measure is important. So I'm trying to explain here that all of the scenarios are somewhat have some problems. And in this case, precision is very important, and it is actually how you measure it. So let me remind you with a real case scenario how things went wrong. So there was an erroneous fingerprint individualization. So there was an error in matching a latent fingerprint associated with the train bombing in Madrid, Spain on March 11, 2004. So if you don't remember the situation in 2004, there was a bombing in a train, I think somewhere between Madrid and Barcelona. And the forensics people recover the fingerprint from the crime scene. And when FBI checked this fingerprint, it matched with somebody in the United States. But the problem was that that person has never been to Spain in his life. Actually, at the time of bombing, he was in United States. So people try to understand why this is the case. And later on, they found the actual person who did the bombing, and the fingerprint also matched with his fingerprint. So the error occurred when a personnel from the FBI latent print unit performed a fingerprint analysis and reported the match of a latent print with a candidate print from a search of the integrated automated fingerprint identification database. So they did this, but the problem is that the consensus of the committee was that the error resulted from the examiner's failure to apply correctly the prescribed ACEV method for fingerprint comparisons. And this method actually refers to the methodology of analysis, comparison, and evaluation verification. So although the methodology was determined to be appropriate, the examiner's application of the methodology was flawed. So people who were doing the measurements or performing the application made a mistake. So in this way, they found a wrong fingerprint. So the FBI's report is available at the link I provided below. If you're interested, you can read the whole situation and technical details how it failed. So let's move on to passwords and password-based authentication. Passwords is a short sequence of characters used as a means to authenticate someone via a secret that they know. Generally, creating an account means choosing a username and a password. So this is actually what is happening in our life. You know, since 1990s, we go to the internet, create an account, and choose a username and a password. The problem is keeping passwords as plain text in a database is a fatal mistake. So in 1990s and until I think 2010, actually some people are still doing this, but what they did was when somebody created an account in the database, they wrote their username and password in the columns that refer to usernames and passwords. But this is a fatal mistake because almost every database leaks at least once. You can always hear in the news that a very famous database leaks, and actually there are web pages that store all of this information, and they measure how many accounts are leaked and so on. So every database leaks. So if you just keep your passwords in a database, then everybody's passwords leaks too. So this is not the correct way of doing it. And here is also a warning I do all the time. In Turkish, there is a translation mistake because password does not mean şifre in Turkish. Okay, password means parola in Turkish. But however, many web pages, many applications, your banking applications, when you just try to log in, they ask you to enter your cipher, şifre, which is not something that actually you can enter. Okay, şifre means cipher, which is actually an algorithm, not something that you can enter using a keyboard. So maybe we can, in the future, correct this mistake. But for the last years, I tried a lot, but realized that nobody's paying attention. But just keep informed. Okay, so there are some password creation policies. You observe it when you're creating an account. For instance, if it is explicit, they say that your password must be 8 characters long and contain an upper and lowercase character, digit, and symbol. So here they actually say what it is. And in this case, attacker also knows this, so they try to attack in this way. And this is also creates a false sense of security because people think that if your password is 8 characters long and contain all of these special characters and so on, people think that they are secure, but actually this is not enough. And I will show you in the following slides why it is not enough and why there must be other precautions that we should take. Or the creation policies can be external, like password should contain 2 parts, such as 2-factor authentication. Generally, we prefer this, especially everybody is using a mobile phone. So having a second confirmation from a device you have is always a good idea, but this is not always enough. For the last year, probably you have seen that a lot of your friends or yours also Instagram accounts are stolen. This is mainly because they ask you to click a link, and when you click it, you have to enter your password and so on. If there's two-factor authentication, since you're thinking that you are logging into Instagram, you also use the PIN that is generated by the authenticator. So this way people capture your account too. So this is also not enough, but a lot better than simply using a password. Sometimes the creation policy is implicit. In this case, they say that if your password isn't strong enough, the system should alarm you to choose another one. But this is really annoying at some web pages because they ask you to enter a special character. You enter a special character, but they think that it is not a special character, so they ask you to choose something different and so on. So some web pages are really hard to create a password for. And moreover, you will forget them anyway, so you will ask your browser to store them. Okay, so let's move on to see how we should store the passwords and why we should store them in this way, because I will talk about what the attacker can do. So as I told you before, we don't store the passwords in the database because if the database leaks, all of the passwords leak. So instead of passwords, we store their hashes. So we use cryptographic hashing algorithms. So I will briefly mention them in the next slide. Probably you already heard about them, but we will talk about what kind of property we need from a hash function. Leakage of the database should not leak the passwords, because if you keep the hashes, only the hashes will leak. Hence, the hash function should be premise resistant, which I will define in the following slides. So in this case, if you don't store the passwords as plain text, but if you keep their hashes, now the attacker can try to perform a dictionary attack or an exhaustive search attack. But before moving on to them, let's recall what a cryptographic hash function is and what we mean by premise resistance. So a cryptographic hash function, actually a hash function H, is a keyless algorithm that takes a variable length input X and returns an output Y of fixed length N. So this is very important. So you're actually giving the hash as Y, which is just a few bytes, a few number of bytes. In this case, N is chosen mostly like 32 bytes, which would be equal to 256 bits. Okay, so regardless of the input length, the output is always fixed. So this is the good thing. For instance, at a crime scene, if there is a hard drive of 8 terabytes, you take the hash of it. So hard drive is 8 terabytes, but your hash output is just 256 bits. So which is easy to use in court, because during the case, if anything changes inside that 8 terabyte hard drive, the hash would not match. So this is why these algorithms are used everywhere, even in the cloud. This is what we are using. When you put a file to Google Drive, Dropbox, or even if you send a picture to WhatsApp, these servers actually store the hash of your file. So if somebody else tries to send the same file, they just look at the hash and realize that they already have it, and they ask you not to resend it. So they're used in many different areas in computer science. So these are the general definitions for a hash function, but for a cryptographic hash function, we expect 3 more properties. These are premise resistance, second premise resistance, and collision resistance. But for the password security, we only require premise resistance, so I will focus on this one. But one thing we want more from a hash function is that we want a hash function to produce random output. So this output Y should also look like a random number. Since it is just zeros and ones in terms of bits, they shouldn't have any specific pattern. This is important, especially in cryptocurrency mining. Okay, so let me give the definition of a premise resistance. Once you are given an output Y, it should be hard to find any input X such that Hx equals to Y. So For this reason, most of the time we also call hash functions as a one-way function. So when you have the input, it is very easy to compute output, but once you know the output, you cannot go back. Recall my earlier example. For instance, this X can be the 8 terabyte of data of a hard drive. From that 8 terabyte, it is easy to produce 256 bits. But then, just by looking at 256 bits, it is almost impossible to guess what that 8 terabytes were, because this is the lossy compression operation. You lose information, so it is not easy to go back. But in most of the time, it doesn't matter which input gave the Y. If you can find something else that also gives this output, it will be enough for you too. So it should be hard to find any X that gives you that output. This is important because the input space is really huge, but the output space compared to this one is small. So there will be many different inputs that will give you the same output. So this will be called collisions. And we want hash function to be secure so that those cases does not happen. So a generic attack like a brute force trial would require 2 to the n operations, and here n is the length of Y. So if it is 256 bits, you can try 2 to the 256 different input, and you expect to hit this Y value at some point. So why this property is important? Because in a password file or a database, using the username and password like this would be a fatal mistake. So instead of doing it, you simply store username and hash of the password. Okay. So if you do it like this, this is actually what people were doing in 1990s. And actually, there are still web pages or government web pages where people still keep the username and password like this. But if you store it like this, this gives you one more layer of security, because an attacker that captures the password file would only capture the hash of your password, which is Y. So in order for them to log in, they need to find the preimage for this output, which is hard if your hash function is secure. And when you're logging in, actually what you do is as follows. You enter your username and password, but the web page you are trying to log in does not know your password. They know the hash of your password. So during that communication, you send your password to them. They take the hash of it and realize that it matches the one that is stored in the database. So they allow you to log in. So this is why any input that gives this output would be enough for the attacker, because even if they don't know your password, if they can find any other X that will give you the same Y, they can try to use it as your password and try to log in, and they will succeed. So this is a good way to provide a little bit more of security, but this is not enough. We will see why in a few slides. But I'm not going to explain the algorithms, but I will give you some of their names and tell you which ones are secure. So in the past, many hash functions are broken. MD4 and MD5, which produce 128-bit output, were badly broken. You can provide collisions in milliseconds or microseconds on a laptop. SHA-1 is recently broken. Just a few years ago, people found collisions, and attacks always get better. So this is why we suggest people not to use SHA-1 anymore. This is very important because I gave a lecture last year to some teachers who teach computer programming in high schools. They thought that MD5 was secure, and they were teaching their students that they can use MD5 for password hashing, which is not the case. As I told you, this can be easily broken. Even the output length is not good enough. And SHA-1 is, as I told you, recently broken, so you should avoid it. If you want a short output, you can use RIPE-MD, which also produces 160 bits like SHA-1, but it is not broken. And other algorithms which produce longer outputs like SHA-2 and SHA-3 can be used. And actually, these are the three things that you should use the previous ones are broken and you should avoid them. This is important because I realized that in Turkish forensic software, the default algorithms for hashing are MD5 or SHA-1. So in the court, they are still providing MD5 or SHA-1 of the devices or the data storages that they found in a crime scene or any place. And actually, they have no credibility in court. So I tried to convince them they shouldn't use them. And I actually recently wrote a report. So probably from this point on, the standards would disallow people to use these algorithms in their devices. Okay. So let's talk about dictionary attack. So I always hoped that it would work like this, but university doesn't allow us to throw dictionaries to each other. So the dictionary attack actually works like this. So assume that people are storing their passwords like this example. Instead of your password, they keep the hash of it. Okay. So what you can do in this scenario is the following: pre-compute the hashes of common words on a dictionary, or their combination with numbers or with combinations of each other. So for instance, take an English dictionary. You can easily get the words from the internet. Just take the hashes of all of these words. Then combine them, take their hashes, add a few numbers to their endings, take their hashes too, add a few special characters, calculate their hashes too. So for instance, if you have an 8 terabyte of hard drive, you can generate 8 terabytes of hashes. So you will have a big set of hash values. And you can sort them. Since these are just numbers, it is very fast to sort numbers. And yes, keep them sorted in a table. Now, the attacker can capture the passwords if their hash values are already in the table. So before performing the attack, you create your dictionary like this. So you have 8 terabytes of, for instance, hashes. So once the database leaks, like here, you end up with a lot of hash values. So now you go to your table and check if any of these hashes are already in your table. So if it is there, then you already know the password. And this way, people capture a lot of passwords, and people are still doing that. And I know that a lot of people still use MD5 for this hash function. So people are still creating dictionaries for MD5 and capturing a lot of people's passwords. So we can actually prevent this happening. The countermeasure for this is the use of salts. So when you create a password, instead of taking the hash of your password, we can also create a random value that we call salt. This can be like 32-bit random value, which is just 4 bytes. And you can concatenate it at the end of your password. So this way, instead of hashing your password, we can take the hash of this thing altogether, password concatenated with the salt. Now, this way, the dictionary created here would not work because you created your dictionary using common words, but not concatenating a random value to their ending. So this way, the salt actually prevents the dictionary attack because attacker has to generate these tables for every salt value. So if you choose a long salt, people generally use 32 bits. This means that there can be 2 to the 32 different salt values, which is, I think, will be more than 4 million. So if you create a 1 terabyte dictionary, now you have to create 4 million terabytes of dictionary, which you wouldn't have that amount of storage. So this actually prevents the dictionary attack. Let me show you a leaked database example, which people were using MD5. You can understand which hash function they are using just by looking at the length of these hexadecimal values. Here, if you calculate, you will realize that this actually belongs to 128-bit value. So from here, you understand that they're either using MD4 or MD5. But MD4 is really old, so you just assume that they are using MD5. And here, this part actually tells you the salt value that is randomly generated when this password was created. So this is also stored in the database. So it is not actually public, but if the database leaks, you capture the salt value together with the hash. Now you have to guess which password concatenated with this salt provides this hash value. So now your dictionary attacks would not work, or you can create a dictionary for a specific target just by using this salt value, but it will take time. And in this case, you would only attack only one person, because in the previous scenario, when you don't use salts, people with the same passwords would have the same hash values. So once you break one of them, you actually break everybody's account who use the same password. And this happens when people use very easy to guess passwords. Okay, so this is how it will look when you actually capture a database. Now, so dictionary attack does not work here, but we can always perform a brute force attack. So we call this exhaustive password searching. So when a hash and the salt value is obtained, you can calculate hash of every possible short password and check if the hashes are identical. So for instance, if you are trying to attack this password, you know the hash value. Just assume that, for instance, the attacker has chosen a password that is 8 characters long. You can try every 8 character password concatenated with this value and calculate the hash of it, then check if that result is equal to this one. So this is what we call an exhaustive password searching. But now the question is, how long will it take? For instance, everybody is suggesting us to use 8 character passwords. So how long will it take you to try every possible 8 character password? This is the question. And since when we are creating a password, they always tell us to, also use a capital letter and a small letter, use numbers, use special characters. So this gives you some feeling of security, but let's see if it really works. For instance, think about an English alphabet. So it has 26 letters. So if you create your 8 character password only using 26 letters, you can generate 26 to the power 8 many different passwords, which equals to this one, but I will show you this as the power of 2. So this number is actually around 2 to the 38. So an attacker who is trying to guess the passwords of people who only use letters will need to perform this many trials. But if they also use capital letters, now the space increases, so it becomes a little bit harder. So if you use numbers, this space slightly increases. But if you allow them to use any printable character in the ASCII table, now you end up with this many passwords. So somebody who is trying to guess your password has to try, in the worst case scenario, 2 to the 52.44 passwords. Now we will talk about how long will it take, but let me remind you this way: we can search the space in a clever way. For example, users select easy to remember short passwords. They almost never use more than 2 special characters. And actually this would be maybe unethical to say, but what people does is, choose a capital letter, then choose small letter words, then put a number, and then put a special character. This is how a lot of people choose their passwords. So this space is not actually this large. Most of the time, you can guess the password a lot earlier without trying all of these passwords. But so the question is, how long will it take to try all of these passwords, right? So let me give you an example. If you have a modern GPU, CPUs are not that fast when you perform parallel operations, and in this case, GPUs have a lot of cores, and each core can try a different password. So a modern GPU can calculate more than 2 to the 33 SHA-2 hashes per second. So in a second, you can try more than this many passwords. And a year contains around 2 to the 25 seconds. So in a year, actually, you can perform 2 to the 58 passwords. So 2 to the 58 actually is larger than all of these. Actually, 2 to the 58 is like 2 to the 5 times larger than this. So this means that using a single GPU, you can try all of this password in maybe 20 days or something. But if you have like 20 GPUs, you can try it in a single day. And if you have 100, then you can make it in a few hours. You can make it even in a few minutes if you have thousands of GPUs. So as you can see, this is not enough itself because this space is not that large. So question is, what can we do about it? Because we can do the following. We can choose our password like 12 characters or 13 characters, but then it will be very hard to remember. We cannot ask all of the users to change their password from 8 characters to 12 or 13. And moreover, most of the systems does not allow us to use longer passwords. Recall some of the systems we are using, for instance, in our university accounts or e-government accounts, you are only allowed to choose 8-character long passwords. So if they're not that large, then we should have a way to prevent them, right? So the solution is to slow down the hash computation speed. Instead of using the hash value of a password, repeatedly use the hash output as the hash input. For instance, you can choose a power of 2. In this case, I gave the example as 8,192. Because this is a default value in some of the Linux versions, but probably nowadays they increase this number. So what I'm trying to show you is this. So in our initial example, we said that we can use the hash of the password. Then we said that instead of that, just use the hash of the password concatenated with salt. Now I'm saying that take the hash of this, but don't put it in the database. Take it as an input and take its hash again and again and again and repeat this process 8,000 times, let's say. So this is actually what all of the web pages are doing. For instance, if you try to log into Facebook, you enter your password. So Facebook actually looks at the salt value in their database. They concatenate with the password you just entered and take the hash of it, and they just check their configuration and see how many times they need to take the hash. For instance, if it is 10,000 times, they take the hash of this value repeatedly 8,000 times, and after the 8,000 times, they look at it and check if it matches with the one in their database. So this way, logging into a web page now 8,000 times harder because it takes this many times more time. But if the computation of the hash is like microseconds, so waiting, slow downing this 8,000 times is not much of a problem. You can still log into the web page in a very fast way. But this way, the attacker job becomes 8,000 times harder because now they have to perform this operation 8,000 more for every password. So choosing this number actually gives you more security, and this number should be increased in the following years because the computational power increases all the time. So before giving a few examples about this process, I will mention a password hashing competition, because at this point you can realize that I'm giving you a way to store password, but this is not a standard or anything, right? This is what we have come up with during the previous years because we have seen what the attacker can do, and now we are suggesting you to use a salt value and take the hash thousands of times. But this is not a standard. For this reason, people decided to come up with a agreed upon method. For this reason, they designed a competition called password hashing, because password hashing is everywhere, and there was an established standard to fulfill the needs of modern applications and to best protect against attackers. So this competition was initialized by Jean-Philippe Almosson in fall 2012. The web page is here. You can check and see which algorithms were in the competition. And you can see that they had received 24 submissions. And in December 2014, 9 finalists are announced. And in July 2015, Argon 2 was announced as the winner. So instead of using SHA-2 or anything, Using an hash function that is specifically designed for hashing passwords might be a good idea. And as far as I know, nobody in practice knows this competition and knows this algorithm, so almost nobody uses this. So this is why I'm trying to inform you that this is a lot better than using SHA-2. Some 4 other finalists also received special recognition. I list them here. Especially LIDA 2 is used in many cryptocurrencies for mining, but I didn't heard of the other 3. So this might be, if you're interested in writing a term project or thesis, analyzing these algorithms might be a good way to start. So let's see some tips for safe passwords. So these are the things actually we need to inform everybody, because everybody are using passwords and not everybody are specialists in computer science. So these are the things they should be informed about. So we suggest that never write down your passwords on paper or electronic sheets. Avoid to always use the same password for every system. This is very important, because if you use the same password you use for your Gmail account and another account, when that password leaks, your Gmail account also leaks. And most of the time, people use their Gmail account for creating other accounts, like your Twitter or Instagram account. So once your Gmail account password leaks, actually you lose everything, and it takes some time to recover all of these systems. Of course, do not share your passwords with anyone. Choose strong, unintuitive, and non-guessable passwords. Use proper software to create and manage strong passwords. Enable two-factor authentication whenever it is possible. Choose non-true answers for password recovery questions. This is really important, because a lot of web pages ask you to choose a password recovery question, like the name of your pet or the maiden name of your mother and so on. If you write the correct answer there, so that when you forget your password, you will rewrite it and recover your password, an attacker can do the same. So try to give false answers to these questions, but also try to remember which false answer you have given to these questions. Finally, change all your passwords whenever a data breach occurs. There are some web pages where you can enter your email account, for instance, email name. So if your email appears in a leaked database, those web pages inform you that such a breach occurred and your email account was also there. So maybe it is a good time to change your password and so on. So try to use that kind of services. I will finish with giving an example about how else we use passwords. We use passwords for key derivation too. So key derivation is important in cryptographic algorithms. We use secret keys. For instance, if you perform full disk encryption on a hard drive, most probably you are asked to choose a password, and from your password they actually generate an AES key, and they perform the encryption using your password that is generated from this password. So idea is to take your password and take the hash of it a lot of times, and the output of this hash function will be used as a secret key. So this password-based key derivation function too is kind of a standard and used in a lot of places. So I will briefly mention what it is. So it takes as the here as it is written, it is a pseudo-random function of 2 parameters. Actually, here you are choosing a hash function like SHA-1 or SHA-2. Then you put your password here. You put your salt value here. Then you choose C. C is the number of iterations that this hash function will be run. I told you that you can choose like 8,000 or 10,000. And this decay length is actually the length of the secret key you want to use in this scenario. So if you want to use AES 256, you just write 256 here. So this algorithm repeatedly calculates hash values and at the end produces you a secret key which has the length of this number. So let me give you some specific examples where this function is used. Actually, in your home, Actually, most of you are at home now, and some of you at work due to pandemic. And currently, probably you're connected via Wi-Fi, and most probably your router is using WPA2, right? So when you have such a system, recall that at home or at workplace, you choose an SSID first, right? This will be how the Wi-Fi is broadcast, and you choose a passphrase for logging in, and this is what you give to people when they come to your home. So as you can see, if we go back here, we had the password and salt, and in WPA2, the passphrase is the password you choose, and SSID will be used as your salt. And here they use SHA-1 in the message authentication code version, and they repeat this process, as you can see, 4,096 times. And at the end, they produce 256-bit output, which is actually used for AES encryption. Okay, so this is how WPA2 works. And moreover, if you use WinRAR, you know, WinRAR is just used for compression, but you can also encrypt your files while compressing them. So in order to do that, you have to choose a password. So WinRAR also uses this function, but as you can see, they use SHA-256. So using SHA-2 is better than using SHA-1. And for this number, they actually choose 2 to the power 15, which is more than 32,000. So as you can see, WinRAR's password security is a lot better than WPA2. So we made an analysis in one of our term projects and realized that if you choose a password that is longer than 8 characters when you're using WinRAR, actually it is almost impossible to recover your password. So this is good for you so that attackers cannot get your passwords, but it is also bad for you because if you forget your password, this means that nobody can recover it. So you have to maybe wait a few hundred years so that the computational power increases and maybe we can recover your password then. But you have to be careful when you're choosing password in this way. So choosing short passwords also might be a strategy here so that if you forget them, you can, you know, perform a brute force attacks and recover them. So by using a GPU, we made the following analysis using WinRAR passwords. So if you only use characters, you know, as the numbers from 0 to 9, and if you choose your password length as 13, it will take 20 years for a single GPU that we used at that time, which is now actually considered an old GPU. It will take 20 years. So if you just choose numbers, small characters, and capital letters, and if you choose a 6-character password, this GPU can try all of these passwords in 41 days. So if you increase it to 7, it will take 7 years. If you increase your password length to 8, it will take 439 years. So adding a special character looks like a better idea. So if you if you use every printable character, which is 94 in the ASCII table, and if you choose your password length as 6, it will take 1.47 years for a single GPU to recover this. This means that this can be recovered easily because if you have 1,000 GPUs, you can recover passwords in a few days if their length is 6 characters. So if you increase your character length to 7, now it becomes 140 years. And if you choose 8-character passwords, now it means that this GPU have to run for 13,000 years to recover your password. So you might at this point say that, okay, 8 characters are enough for me because nobody would, you know, run a GPU for 13,000 years. But now recall that modern GPUs are maybe 8 times faster than this. So let's say that it is 10 times faster than this. So it will take maybe 1,000 years for a modern GPU to recover this password. So you might again say that, okay, 1,000 years is longer than my life. But if somebody uses 1,000 GPUs, this would mean that they will recover your password in a year. So this is why I'm saying that if somebody is really determined, they can capture 8 character passwords. But so for this reason, if you choose something larger than 8, like 9, it will be almost impossible with today's current technology to recover your password. So this is why we said that it is enough to choose passwords larger than 8 characters and you will be secure. So this is important, as you can see, even for WinRAR, which is really good because they take the calculate the hash value more than 32,000 times. But now the question is, how many times other systems take the hash of the password, right? Because a lot of databases leak, and when they leak, you hear announcers saying that, okay, our database leaked, but don't worry, we used cryptographic precautions. We used the SHA-256 so that your passwords are secure. But the question is, how many times did you use SHA-256? It's a short number, like maybe 4,000. Then if I have a password that is short or easy to guess, then an attacker can capture it in a few days. But if they had used the repeated the hash function more than 30,000 times, then I can be confident. So for this reason, whenever the database leaks, even if they say that they did a good job storing your passwords, and if you had already chosen a good password, there is no harm in changing it anyway. Changing a password just takes a few seconds. So whenever a data breach occurs, if your account is also in there, just simply change your passwords. This way, you can avoid attacks that will happen in the following months or years. Okay, so that will be all for passwords.